so now we're going to get into a discussion of acids and bases and how we go about naming them. So before we get to the actual rules for naming these compounds, let's talk about some general properties displayed by these substances. So first thing that is mentioned here concerning the properties of acids is that they taste sour. Now, let me just say here that that does not mean that you should start tasting liquids in the lab to find out whether or not it's acidic or basic, all right? That would be a very dangerous practice to engage in. But actually, in our everyday lives, when it comes to consuming certain foods, we actually have tasted acids and can confirm that it's actually a substance that has a very sharp sour taste. I'm talking about, for example, fruits. If you have consumed, any citrus fruits like oranges, etc., then you would have consumed some acids. Actually, one particular acid known as citric acid. So that's one example. Another example is anything that you have added vinegar to contains acid, because vinegar is actually 5% acetic acid. So those are just two examples of acids in our everyday lives that I'm quite sure you guys have tasted and can confirm that they have a sharp sour taste. Another property of acids is that in some cases, especially for the mineral acids, they produce a very stinging and pricking sensation on the skin. And that's largely due to the fact that the hydrogen ions which is produced is what causes that sensation. And then one important property of an acid that is used in terms of indicating its presence is the effect on litmus paper. And basically, litmus is a substance which takes on a particular color depending on the acidity or basicity of its environment. So typically, if you want to test for acidity, we use the blue version of the litmus paper, and then we dip it in the acid, and if it becomes red, then we know that the solution is acidic. Another property of acids is that it reacts with many of the more active metals to produce ionic compounds and hydrogen gas, all right? And then the final property listed here is that acids will react with bases and therefore will lose their acidic properties. And we call that reaction a neutralization reaction, which we'll talk about later on, all right? So those are just basically a list of the common properties displayed by acids. And then when we look at their chemical counterparts, bases, these are the properties associated with them. They tend to taste bitter. Again, please do not taste any substance in the lab to figure that out for yourself. They tend to feel slippery or soapy on the skin. Again, this is something I would not expect you to practice in a lab. But if you accidentally get some sodium hydroxide, for example, on your skin, it feels soapy. And the reason why is because actually what happens is that there's a reaction that takes place between the sodium hydroxide and the components of the oils that is secreted by your skin. It actually converts it to soap. So therefore, that's why it feels soapy, all right? The next property listed here is that, again, it has to do with litmus paper. As I said before, to taste for acidity, you would use blue litmus, it becomes red. But if you want to test for basicity, then you would use red litmus and it would turn blue, all right? And then the last one is basically the same as the last line I mentioned with regards to acids. They tend to react with acids according to the neutralization reaction, which I talked about earlier, all right? So those are just some properties displayed by acids and bases. So this brings us to the question as to what is an acid and what is a base? And the honest answer is it depends on who you ask, right? Because it turns out that there are different definitions of acids and bases. And in some cases, the definitions reinforce each other, but in other cases, they don't, all right? Now, the particular definition that we'll be looking at here is the one according to this guy by the name of Arrhenius, a very important figure in chemistry because of a lot of work he has done in terms of basically helping us to understand the nature of acids and bases, for example. And also, he was the first one, if I remember correctly, who determined the presence of ions in solutions, which would be responsible for the electric current flowing through it. So he did a lot of work for which we are indebted we're indebted to him for what he has done. Okay, so as I said before, there are several definitions for acids and bases. So Arrhenius, he came up with his own definition, and his definition says that for an acid, it's a compound which, when dissolved in water, ionizes to form a solution which contains hydrogen ions and some other anion, all right? And on the other hand, Arrhenius base is a solution or compound that, when added to water, forms hydroxide ions in solution and some cation, all right? So that's basically Arrhenius's definition of an acid or base. Well, and base. And then neutralization is what we talked about earlier. That is a reaction between an acid and a base to form a water and the other product, which will be a salt. And later on, we're going to learn more about neutralization reaction. But for now, we're just going to leave it at that, all right? Oh, and by the way, a salt is the combination of the cation from a base and the anion from an acid. So what we're going to look at is basically the general formulas for acids and bases, and then you can understand from that how the formula for the salt can be arrived at based on the reaction between a particular acid and a particular base. So what we're going to look at now is how do we name acids? And there are several approaches one can take in order to understand how acids are named. So what I'm going to do is I'm going to start off with a discussion of the binary acids. So I'm going to open up this right here, and I'm going to talk about binary acids. How do we name binary acids? Okay, now before we talk about binary acids, I'm going to talk about binary compounds, binary molecular compounds containing hydrogen. All right? And I'm going to mention a few examples in this discussion. All right? So, for example, hydrogen chloride, this is the formula for it, all right, exists as a gas, right? Now, when it comes to naming these compounds, right, we do not use any prefixes whatsoever, right? We just simply name it hydrogen, and then the stem of the name of the other element, and then IDE, all right? So the name of this compound is hydrogen chloride, all right? Here's another example, H2S, which is also a gas. The name of this compound is hydrogen sulfide. All right, so these are two examples of binary molecular compounds that contain hydrogens, all right? Now, if you were to add these compounds to water, right, you're going to get an aqueous solution containing these substances. So this becomes HCl aqueous, and if you do the same thing here, this becomes H2S aqueous, all right? And it turns out that these solutions are acidic, all right? So they behave like acids. And as such, because they're acidic, these now will have a different name compared to the compounds from which they're formed, right? So how do we name these compounds is dependent on the name of the original binary molecular compound that you started off with, right? So according to the rules, and this is the IUPAC rules, the names of binary acids always starts off with hydro, right? Hydro. All right? And then the next part of the name of this compound is the stem of the name of the other element. So in this case, it would be chlor, and in this case here, it would be sulfur. And then the end of the name is going to be ending with ic acid. So in this case, it would be ic acid. In this case, it's going to be ic acid. So therefore, in this case, the name of this compound is going to be hydrochloric acid. In this case, it's going to be called hydrosulfuric acid. So when it comes to binary acids, they always start off with hydro in the beginning, and then the next part is the stem of the name of the other element. In this case, it's chlorine, so we have chlor here. In this case, it's sulfur. So in this case, you actually use sulfur here. And then the ending for both cases is going to be always ic, let me put it in boxes, acid. Ic acid, all right? So that's basically how we name binary molecular compounds, all right? And it's very important that you recognize, as I said before, that there's a difference between the pure substance before you add the water or before you add it to the water and the solution that is formed after you add the water, right? The names will be different because they'll be different substances, so to speak, because one will be in an aqueous solution, which is acidic, the other one would not be, and therefore it's not considered to be acidic in that state, all right? So that's basically how we name binary acids formed from binary molecular compounds containing hydrogen. So let me go back to the PowerPoint here and show you a couple of examples. So this is the first example that I did just now. The name of the acid is hydrochloric acid. In this case, here's the other one, hydrosulfuric acid. So those are the two obvious binary acids in this list here. I don't think there's any other binary acids listed here. Okay, so that leads us now to the other type of acids known as oxyacids. So in the case of oxyacids, one way of looking at naming them, let me go back to my writing software here and clean this up. So one way of looking at how we name them is that we look at the name of the corresponding anion, all right? So I'm going to use a couple of examples. So I'm going to use the anion, okay, let me use NO3 minus, right? The name of this anion is the nitrate ion. Of course, you can look this up in the tables that I've provided for you, all right? And then let me use another example here, NO2 minus, right? And the name of this ion is the nitrite ion, all right? Okay, now, one can derive the formula for the corresponding acid by adding to each of these the number of H plus ions equal to the number of negative charges present in these cases. So in this case, you have one negative charge here, so that means you add one hydrogen ion to that, and the resulting formula will be HNO3, right? Do the same thing here. You add H plus to the NO2 minus, you're going to end up with HNO2. So these now are what we call oxyacids, oxyacids. So now we're going to look at how we name these acids. So in the case of the first one here, the name of this anion here ends with ATE, right? According to the IUPAC rules, to name the corresponding acid, we replace the ATE with ic acid. So this becomes nitric acid. All right, so the ATE ending is replaced with ic acid, and that's how we name the corresponding acid from the anion from which it is formed. So that's what happens in this case. Now in this case here, the ending of the anion here is obviously ITE. That's a nitrite ion. So according to the rules set forth by IUPAC, the way we name the corresponding acid is we still start off with the nit, but instead of ic, you're going to have OUS and then acid, right? So the name of this acid becomes nitrous acid. So the ITE ending in the name of the anion is replaced by the OUS acid ending in the name of the corresponding acid, all right? So key thing you need to remember from this is that if the anion ends with ATE, the acid name, the corresponding acid name ends with ic acid. If the anion name ends with ITE, then the corresponding acid name ends with OUS acid. All right? Okay. The next example I'm going to do here is SO4 2 minus. And in this case here, because there are two negative charges, we add two H plus ions, and therefore the corresponding formula for the acid is H2SO4, right? The name of this ion is sulfate. And if you remember what we said here, the ATE ending is replaced with ic acid. The same thing applies here, slightly different because the name of this acid will now become sulfuric acid. All right. And then in the case of SO3 2 minus, for which the name is sulfite, to get from that to the corresponding acid, again, we add two hydrogen ions to get H2SO3, and therefore the name of this, I'm sorry, SO3, not 4, and therefore the name of this acid, according to the IUPAC rule, if you remember what we did here, ITE is replaced by OUS acid. Same thing happens here. Sulfurous acid would be the resulting name because it is formed from the sulfide ion. So 8 to ic acid, ite to OUS acid. All right. So that's basically how we name oxyacids. All right. Okay, now there's one more thing I need to talk about when it comes to naming acids. Now there's one particular acid which is kind of outside of the, how should I put this? It's not binary, but at the same time it's not an oxyacid, right? So it's kind of different in terms of its combination. So we have to kind of treat that differently. So let me clean this up here. And let me just deal with this particular acid. The formula for this acid is HCN aqueous, all right? Now, as I said before, it is not a binary acid because it is made up of 3 elements, hydrogen, carbon, and nitrogen, all right? It's not an oxyacid because there's no oxygen present in this acid, right? So this has to be dealt with differently in terms of how we name it. So let me explain how we arrive at the name of this acid. Now, this particular acid can be formed when this gas, hydrogen cyanide gas, is added to water, all right? Now, let me just say that this gas, you don't want to be in a room filled with this gas. It's toxic. It basically reduces the ability of your oxygen to transport, your blood to transport oxygen to the cells. So if you inhale it, you'll die almost immediately, all right? So this is called hydrogen cyanide, all right? Before you add it to the water, all right? So when added to the water, excuse me, this is called hydrocyanic acid. All right. So what IUPAC decided to do is that they treat this, for the purpose of naming it, they treat it as a binary acid. But as we said before, it's not binary, right? It's not a binary acid, but, you know, because it's kind of unusual, it's not binary, but at the same time, it's not an oxyacid. IUPAC decided, okay, well, you know what? We'll just treat this as a binary acid for the purpose of naming it. And then based on that, then we can figure out the name of the corresponding acid, which is the hydrocyanic acid. So that's basically how we come up with the name of this particular acid. Okay, so that's basically it as far as discussion of acids are concerned, and also for this chapter, all right? So the next chapter, of course, is going to be chapter 4. So chapter 3. So the next video I'm going to post up will commence with that particular chapter, all right?